If we have simple numbers for the order, it turns out that there are a set of integrated rate laws that can be developed. In the case of first order reactions, we're going to talk about the integrated rate law. We've been doing this where we had multiple experiments with different initial amounts of reactants and using initial reaction rates, and we've been doing our problems that way. But it's also possible to do this if you have only one reaction and you've been keeping track over time of what's going on. This comes from a concept in mathematics, specifically in statistics, called ergodicity. It is kind of an interesting thing to think about, the fact that you could have multiple experiments with different initial rates and different initial conditions, and yet you could still do the same thing over time with a single experiment instead. And once we start talking about examining it over time, that's where we're able to do something with an integrated rate law. In this case, we're talking about a first order reaction. So this is a case where the reaction depends only on the concentration of one reactant, and we can use an integrated rate law to model it. Now, here is the rate law, an integrated rate law for a first order reaction. It was derived with calculus, so I'd just like to show you what is going on there. If we had a first order one, it would be because we came up with rate equals K, and in this case, the concentration of ozone, just to the first power. That's a first order rate law. This could also be written in terms of the O3. That is decreasing, right? Because it's a reactant. So I'm going to have to change it so that I'm saying the rate of the reaction. I'll change the sign, and it would be the change in ozone over the change in time. So this is what I am starting to work with. Now, here's the thing that I can do. I can say to myself that the independent variable is time, and the dependent variable is the concentration of ozone. It could be of anything, but in this case, it's of ozone. So I can take this and rearrange it. I'm going to put all the ozone things on one side and all the time things on the other side. So minus K delta T equals delta of ozone over ozone. I don't want a delta T, so I'm going to integrate both sides, 0 to T. And I would end up with minus KT equals the natural logs. If you have done calculus, you would realize this is a natural log of the content, T content of 0, which is also equal to the logarithm of the ozone at time T minus the logarithm of the ozone at time 0. We'll go back to thinking about it. If it was a general one, we'd say, okay, instead of saying ozone, we're just going to say it's something X in this case. So natural log of whatever it is would be equal to, and now I'm going to pull this over here, minus KT plus the natural log of the substance at time 0. We've left off the T, it's implicit. I'm trying to figure this out at time T. I could start with the original and see that it's going to reduce. And you can see then that it would generate a line where this would be the slope and the y-intercept, in other words, B, would be the natural log of the reactant at time 0. So this is the sort of thing they do in order to develop these integrated rate laws. I just wanted to show you how one was done. The important thing is knowing what to do with that.